Hello and welcome to another edition of Math Teacher to Go. Today we're going to look at functions. This is the first part of 3 videos that talk about functions and function notation. Today we're going to work with the idea of domain and range, and we're also going to look at the idea of, whether a relation it represents what a function. So there'll be some vocabulary here, and then we're going to look at that when we're given a set of points that's a relation, or how do we tell if a relation that's given as a graph is a function, or how are we going to tell if a relation given by, and this word polynomial isn't necessary by any equation represents a function. A polynomial is a specific kind of function, and actually polynomials generally are functions. So as we go through this, I want to remind you that math isn't just equations. A set of points would be math as we call numerically. We can look at math 4 ways: numerically, graphically, and my handwriting isn't great there, sorry. Algebraically is what most people commonly think of as math, because that's with equations. And the other way we look at math is verbally, which we're kind of doing now. All right, so first of all, what is a relation? That'll be the first thing we look at. I'm going to try to pick up a different pen here. So a relation is any set of ordered pairs. Well, what do you mean by ordered pairs? Well, ordered means what comes first, what comes second matters. The order is important. You can't just interchange them. And pairs means there's 2 things. So I was going through my cabinets in my kitchen one day when I was thinking about writing these, and I looked at some packages. I looked at a cheese stick, and I saw it had 90 calories. So that made an ordered pair, the cheese, 90. And this little squiggly bracket here just means these things make a set. This set is my relation. You don't have to worry too much about that. Then I looked at a bag of popcorn and found it had 100 calories. Then oatmeal had 150. Muffin, it was an English muffin, I think, had 120 calories. And a serving of rice had 150 calories. So that's my relation. The food is related to the number of calories. So as I looked at that, I made a relation. So, and here's another kind of relation you might get from a set of points on a graph or something. -4, 2 is a point. -1, 3. These are things you're more used to seeing in math class. This is also a relation, and it's in set brackets to indicate it's a relation. So there are some vocabulary words having to do with relations. And the first word, and this comes up over and over again in mathematics, is domain. It's the set, so we're going to make a set containing only the first coordinates of an ordered pair. So the domain for example 1, is, I'm going to make a set. I'm not going to be too fussy about this when you give me the domain, but I'm going to list the first of each ordered pair, and in this case that was the foods. So I have cheese, I have oatmeal, O-A-T-M-E-A-L, I have popcorn. Okay, so look, I mixed up the order, but that doesn't matter as long as each item is listed. And it only gets listed once. If it were to appear twice, it would only get listed once. Muffin and rice. Okay, so I just listed the first of each. I mixed up the oatmeal and the popcorn, but that doesn't actually matter. And I put a set bracket at the end. So that's the domain of example 1. For example 2, I list all the numbers that appear in the first position within each of those parentheses. I get a -4, and when you list a set, you separate the elements of the set with a comma. -1, 0, 1, -1. Oh, I don't need to write the -1 again. So I'm going to see if this will switch to an eraser for me. There we go. See if I switch it back to a pen. Yep, and I can just put my brackets. So the domain of example 1 was all the foods. The domain of example 2 was the first number in each ordered pair, but the -1 appeared twice, so I don't need to write it twice. It's already there. So the next word we look at is range. A range is the set containing the second coordinates. Sorry about that. The second coordinates of the pair. So in the case of example 1, it looks like I had 90, 100, 150, and 120. So I'm going to, for example 1, 90, 100, 150, and these are the calories. They appeared twice. 120. Then there was another 150. I don't need to write it twice. This is the range of example 1. Of example 2, the range will be the list of the coordinates that appeared second. Looks like I have 2, 3, -2, -4, and 5. So each of those appear as elements of the range. Let me check my work. Sometimes I forget. There we go. Okay, so that's the range of example 2. So those are the first two things you have to understand. Domain means the list or the set of all of the items that are before the comma in each set of parentheses, the first part of the ordered pair. And the range is a list of all the second parts of the ordered pair. For example 1, the range was the number of calories. So once you understand that, we can start to talk about the idea of what is it about the domain that says I have a function or I don't have a function. All lists of ordered pairs are relations, but they have to meet another criteria to be a relation that's also a function. Now this is a textbook description. A function f from set A to set B is a rule of correspondence that assigns each element of x in A to one element of y in B. So the x is your domain, the y's are your range. And set A is the domain or the set of inputs, and set B is the range. Now, in order for a relation to be a function, each member of the domain must show up only once. It can only have one member of the range. So if you look at our two examples, only one of them is a function. Let's go back to our examples. Example 1, we look in the domain cheese, popcorn, oatmeal, muffin, rice. Nothing was repeated in that first piece of each pair. So that one is a function. Okay, so that is a function. But if we look at set 2, and I'm going to erase these other marks, example 2, which is a set, I have -4 as part of the domain. I have a -1, I have a 0, I have a 1, and then I have another -1. Because -1 appears twice in that first position, example 2 is not a function. Sorry, I'm still getting used to this pen. It's not a function. There we go. So the easiest way to tell with a list, when you have a set of ordered pairs, that's your relation, is you look to see if any of the first elements of the pair are repeated. If none are repeated, your relation is a function. If you find one that's repeated and has a different value of y with it, this one is a 5, then it is not a function. You could have -1, 3 listed twice and it would still be a function because -1 still only goes with 3, but you cannot have 5. If I say for this list x is -1, what's y? You would tell me it's either 3 or 5. The fact that there's a choice for the y means you don't have a function. If any one x value has a choice of y values, has more than one y value, your relation is not a function. So that is the big idea here. So example 1 is a function, example 2 is not, because example 2 has the -1 show up twice in that first position. Now, what if we change the order? Here's a way to represent the function I gave you for example 1 graphically. The domain is in this greenish blue box. That's the list of all the foods, and those appeared first in example 1. Here's the list of the calories. So if you notice, I draw an arrow. Cheese had 90 calories. Rice had 150. And you can see there's 2 arrows pointing to 150. That's not a problem. If I see a graphical representation of a function and each item in the domain, which is generally on the left, only has one line leaving it, it doesn't matter where that line goes to, as long as it goes to something, it is a function. But what if I swap the domain and the range? And when we do that with a set of points, we're actually taking something called the inverse. That comes up later, but I'm just going to swap. So now my domain becomes the list of calories, and my range is the list of food items. Now look, if I said the calories are 90, what's the food? You would immediately say cheese. But if I say the calories are 150, you look and say, oh, it's oatmeal or rice. The fact that there's a choice, when I give you this element of the domain, that you have a choice of the range, means this is not a function anymore. So when the food was the domain, it was a function. So it doesn't matter if the range is repeated, but if the domain is repeated, you have issues with it being technically a function. So that brings us to this statement, where a function is a relationship between two sets in which the set of the domain has one and only one item it corresponds with in the range. So this is the nuts and bolts of how you figure that out. If you don't see any value of the domain, the things listed first in each pair, listed more than once, you have a function. If it's listed more than once and has a different value of the domain with it the second time, then it's not a function. I'm not going to trick you by putting down the same point twice. You're just going to need to look and see if the x's are all different. So I want you to pause the video and complete the following problems. I just want to know whether these are functions or not. Don't sell yourself short by watching it before you try. It's much better to try, even if you really don't feel like you know what you're doing, because then the explanation will make more sense. So stop the video and come back and when you're done, and I will help. We will go through these. Try problem 1 and problem 2. Okay, you're back. So I assume you tried these. Now, is this relation a function? I gave you a set of points. So the way you answer that question is you look at each of the first elements. You get a 4, 2, -2, -3, 0. None of those first parts of each pair were the same. So this is a function. So let's look at the second problem. Again, you have a set of points. What I'm talking about here, the big idea that no x has more than one y, or no piece of the domain, no element in the domain has more than one element in the range. That's true for all forms of the relation. But right now we're talking about when you have a point, when you have a list of points, what do? You look at the first part of -2, 5, 5, oh, and I have a +2, and I have a -2. Those are different numbers. So I can stop right there. This is not a function. Doesn't even matter what the rest of it says. As soon as I find 1, I have something that violates the rules of a function. So that's nice, but we don't always get our functions as sets of points. Often we get them given to us as a picture or a graph. So when we represent a relation on a Cartesian graph, that word Cartesian just means our usual XY coordinate system. You're used to seeing that. We are plotting a series of points. They might be an infinite series and we connect them with a curve, but it's still a series of points. The X coordinates of the domain and the Y coordinates of the range. Now sometimes students have trouble figuring out, remembering which is X, which is Y. So write X and Y in alphabetical order. Now write domain and range in alphabetical order next to that. And now you have X is the domain, Y is the range. That's one way to remember it. If you have other ways to remember it, I'd be interested in having you share them in class. So this is a graph of the points from our previous list. For example 1, I think, for what we just did. Problem P1 that you just did. And we decided P1 was a function. And if you look at this, if I draw lines, let me get a different color pen. Oh, that's not a different color pen, that's an eraser. All right, I have a blue pen. If I draw a vertical line, and I'm going to do my best job, this grid right here is a vertical line. Through any of these points, I will never pass through another point. So that's because each of the X coordinates are different. The vertical lines really are all the points that would have that X coordinate. And you see I do that through each point, and I will not pass through another point. So that is the way on a graph that I can tell that each X has only one Y. There's no vertical line I can draw that passes 2 points. So if you look at this, all the X coordinates of these points are different. You could write out the coordinates of the points if that's easier for you, but you don't have to do that. You get a very quick answer visually. So let's go down. So this is where I explain that because this is a function, there's no vertical line that will cross twice. Then if we go to practice problem P2, which we decided was not a function, you can see that if I look at this grid line here, which is a vertical line, it passes through 2 points, this one and this one. That only needs to happen once to say it's not a function. And we say this has failed the vertical line test. So when you have a graph, even if it's not just a graph of points, this is the test you use. Is there any place on this graph that I can draw a vertical line and cross the graph, in this case the points, twice? In this case, yes there is. So if there is, you fail the vertical line test. And I don't think I wrote the word test here. So what if we have more usually we get a graph that's not a set of points. So if I drew a vertical line at x equals 5, which I did, I would see I pass through 2 points. So what if our graph is not just a set of discrete points? What if it's a continuous, like a polynomial, like this is a quadratic? Well, if I say, is this a function, the way you answer is you look. You look at the graph and you see, is there any place, and it doesn't have to be on a grid line, it can be any place, that I can draw a vertical line and touch it twice. In this case, there is not. This keeps opening up and each x value is different. So you literally look. But now if I turn that sideways, and I don't need to find more than one, but so I draw a line here, and this touches here and here, and this is not a function. Okay, because I failed the vertical line test in many places, but I only need to fail it in one place. So parabolas, upright parabolas are functions, sideways ones are not. So I want you to try the next two examples. I think there's two. No, yeah, there's two. Try 3 and 4 and tell me which one's a function, or if they're both functions, or if they're both not functions. Stop the video and come back. All right, so you've tried the problems now that you're back. Problem 3 looked just like our first example above, and there's no way I can draw. I'm not drawing very good vertical lines, but any vertical line will only touch in one point. It's a pretty thick point because I've drawn this graph thickly so you can see it. But this is a function. So problem 3 is a function. We go down to problem 4. We have a circle. Now the equation of a circle is something like x minus the center point squared plus y minus the y coordinate of the center point squared, and that's equal to the radius squared. You may have seen that somewhere. I could find the equation of the circle, but you're going to notice is the x part is squared and the y part is squared. But on a graph, what you notice is there's many vertical lines that touch more than once. Even if I just look at grid lines, I've got grid lines that touch more than once. So a circle is actually not a function. It's something we call a conic section that you may see later. But the graph of this circle is not a function. It has an equation. I could find the equation for that, but it is not a function. So what if I have an equation? How do I figure that out? Do I have to graph everything? No. If you can get y by itself and it only has one calculation to give you one possible answer, then your equation represents a function. Let's take this equation, x squared plus y equals 4. That's actually going to be a parabola that tips upside down. I know that because I teach a lot of math, but at some point soon you will also know that. So I have a squared value on the x, no exponent on the y, which means it's a 1. If I solve this for y, I get y equals 4 minus x squared. And no matter what I put in for x, that's silly. No matter what I put in for x, I will get a single number as an answer for y. Now, those numbers might repeat. If I put in x is 2, I get 4 minus 2 squared, which is 0. And if I put in x is negative 2, I get 4 minus 4, which is also 0. That's okay. But in each case, I just get one choice for y. When x is 2, y is 0. No choices. When x is negative 2, y is 0. No choices. So this makes that a function. And if you look at this, the exponent on the y is odd. It's a 1. Okay, y to the first. If your equation has an odd exponent on the y, it is a function. If it has even exponents or odd exponents on x, that doesn't matter. But on y, as long as you don't have any even exponents on the y, it is a function. That's a quick, simple, it's kind of simplistic right now, but it works for what we'll be doing. So here is the graph of that function. You can see it passes the vertical line test. Now let's change one thing. I changed the y to y squared. Now I have a circle of radius 2. If you studied circles before, you might remember that. But if you don't, let's look at how the algebra works. And the reason this is difficult for students is a classic algebra mistake that everybody makes, and I even occasionally do it even though I know better, thinking you only get one answer. But if I were to isolate the y here, I subtract x squared from both sides, and that gives me this. Now, I want y by itself. I don't want y squared, so I take the square root of both sides. But when you do that, you really only get the absolute value of y, because once you square a number, if you square 3, you get 9. If you square -3, you also get 9. If I tell you the square of your number is 9, your number could have been either one of those, but you do know its absolute value was 3. So this is really, when you take the square root of both sides, you're really getting the absolute value of one side. So if the absolute value of y is this, it means y was either the square root of 4 minus x squared, or it was the negative of the square root of 4 minus x squared. That is 2 possibilities for one x. Any x I put in, I have to calculate the positive square root of 4 minus x squared as well as the negative, and I have a choice for y. So this is not a function. In that absolute value, when you take the root of both sides, only happens when you're taking an even root, like a square root of 4th root is 6th root. So because the y was squared, it was an even exponent, I get this situation here, and therefore it's not a function because I have to have 2 answers. Now, many of you are saying, well, wait a minute, the square root of a number is just a positive. Yeah, but if I say x squared equals 9, what's x? There are 2 possibilities. If I say what's the square root of 9, this is what we call a principal value. Every arithmetic problem has one answer. Algebraic equations can have multiple answers. We don't say the square root of 9 is 3 or -3. It is 3. But I'm not asking you here, I'm not saying what's the square root of 9. I'm saying give me all the possible numbers I can replace x with and get 9. That's a different question than asking you what's the square root of 9. That's why we often forget that there's 2 answers to the equation, because there is only one square root of 9. So, I went back a little, sorry. So here's the graph, that green one. There we are, the green graph. Sorry if I made you dizzy. Is the circle x squared plus y squared equals 4. And you can see it's not a function because somehow I've lost my pen. It's not a function because it fails the vertical line test. So you can see if I look even just at the x-axis, the y-axis, sorry, it touches twice. So this one fails the vertical line test if you look at the graph too. So an equation is a function if there's not an even exponent of the variable that represents the range. In this case, the range was y. So pause the video, and there's 2 equations here. I'd like you just by observation to tell me if each of them is a function or is not a function. So you can stop the video now, and we'll be back in a moment. Okay, you're back. All right, let's look at problem 5 here. I have a 2 for an exponent on the x and I have a 3 on the y. This is a function. There's no even exponent of the y. I could solve this and get y by itself without having to put a plus or minus in front of the radical. And that's because you can take the cube root of a negative number. Taking the cube root of both sides gives you a unique answer. So because that's a 3, now if that had been a 4 or a 6, then I wouldn't have had a function. This exponent of the x doesn't matter to whether or not it's a function. When I look, so this one was, yes, it is a function. When I look at problem 6, I see I have a fourth power. If I were to solve this to isolate y, I would have had to add 5x squared to both sides, and then divide both sides by 3. And then if I want y by itself, I can see I'm going to have to take a fourth root. And when I take a fourth root, and that's how I tell it it's a fourth root, and that's how I tell it's a fourth root, I have to take both realize that I've lost track of the sign, because when you multiply a number by itself 4 times, you always get a positive number. So I have to get the positive of whatever's in that root as well as the negative. Those are 2 possibilities. So because this is an even number, and even numbers are numbers that end in 0, 2, 4, 6, or 8, and it's on the y, this is not a function. And I think that's all we have in this part of the video. If you want to learn more about functions, look at part 2 and part 3. And that's all for today on Math Teacher to Go.